Okay. So where we left off, in first order, linear systems is that if we have y prime equals matrix A times y plus some vector value function b of t, then if A is known to be diagonalizable, then we have this solution formula that's similar to the case of a single equation. Y of t is e to the at y of 0 plus integral e to the a t minus s b of s ds, where e to the at is defined as a Taylor series. But is also was shown to be equal to p e to the dt p inverse, where A equals PDP inverse is a decomposition of A, where D is diagonal. Okay. So if this decomposition, so the diagonal matrix D holds all the eigenvalues of A, and the columns of P are the eigenvectors of A. And with the assumption that A is diagonalizable, that means that A is known to have n linearly independent eigenvectors if A is n by n, and that's why P is invertible. Okay, so what if A is not diagonalizable? Because what happened in the diagonalizable case is the original system of n ODEs was decomposed into n scalar ODEs that were independent of one another. And so we used the formula for solving a single ODE to solve those, and then we got back to this from a decomposition of A. So we'd like to be able to do something similar in the case where A is not diagonalizable. So can we actually do that? So this decomposition of A does not always exist. So we want to work with a decomposition of A that that does always exist. So so we'll get the decomposition we can work with that is as close as possible. Okay. Okay. All right. Hold on a second. Okay. Okay. All right. So A is equal to, well, I'll give the name of it first. The Jordan canonical form, which I did bring up, I believe, briefly in Math 610. So A is equal to xj x inverse. So this is as close as we can get to PD P inverse when that composition doesn't exist. And J has this form, J1, J2, Jp. It is not a diagonal matrix necessarily. It is a block diagonal matrix. And each block has this form, has an eigenvalue lambda I going down a diagonal. It is upper triangular, so zero's down here. And then we have a super diagonal of all ones. So this is the quintessential non-diagonalizable matrix. So if you have a matrix like this, there's no way you can multiply by P on the left, or P inverse on the left, P on the right, to make it diagonal. So this is called a Jordan block. All right. So there are certain manipulations that were done last time in a diagonalizable case that can be carried out in much the same way here, because notice in both cases we have what's called a similarity transformation. Here I'm multiplying by the matrix on the left and its inverse on the right. A similarity transformation that preserves eigenvalues. So, so here's what we can do.
May I ask a quick question?
Yeah.
I'm just trying to recall from last class to the 610 or whatever, but so you have the ones down that diagonal. It's zeros above that?
Oh, yeah, I forgot that, yeah.
Okay, I was just making sure it wasn't more ones.
Oh, no. Just,
Okay.
Yeah, I forgot about that part. Okay. So if I define a change of variable, just like last time, W is equal to X inverse Y. Then my original system of ODEs over there becomes W prime is equal to JW plus the source term C of T, where C of T is equal to X inverse B of T. Now, that is the exact same reduced system of ODEs as last time, except I had the D here, and then P was a transforming matrix instead of X. The difference is this does not separate the original system of N coupled ODEs into N independent ODEs. They're not all decoupled. Now, in the case of Jordan blocks that are one by one, yes, those equations are separated from the rest. But you're going to have situations like this involving these larger diagonal blocks where you have some of these ODEs are still coupled together.
Since I forgot my glasses.
Oh.
I almost see everything.
Oh.
That is X inverse, right?
Yes.
Okay.
All right. So what I need to do now is illustrate what that looks like. What kind of ODE system do we have now? And then, since they're not completely separated, how do we solve it? All right, well, first, any questions about what's written here before I continue? Okay, so let me give an example, say like a system of 5 equations. And see how that proceeds, and then extrapolate from there. Let's suppose our Jordan form looks like this. Lambda 1, lambda 2. All right, and I'll section off the blocks. Okay, so here we have a 5 by 5 system matrix for a system of 5 ODEs, and there are 3 Jordan blocks. So the first 2 blocks for lambda 1 and lambda 2 are just trivial 1 by 1 blocks. And then we have a 3 by 3 Jordan block corresponding to another eigenvalue lambda 3. Now, the eigenvalues may actually, they're not necessarily distinct. Like you could have a same eigenvalue associated with more than one Jordan block. That accounts for cases where like an eigenvalue may repeat a certain number of times, but have fewer linearly independent eigenvectors. So the number of Jordan blocks that you have is equal to the number of linearly independent eigenvectors you have in total. So here we have a 5 by 5 matrix, but there's only 3 eigenvectors. And then you'd have 2 generalized eigenvectors to complete the set. And that makes up the matrix X in the Jordan form.
What about the only thing I think that's throwing me off is the why just ones in the lower block?
Oh, okay.
I guess we don't really care about what else is happening.
Yeah, I just want one interesting example. So this would be a case where this eigenvalue is in a block by itself. It has an eigenvector. This one has an eigenvector.
Okay.
And then this 3 by 3 block has only one eigenvector that goes with it.
Okay.
And 2 generalized eigenvectors. But these 2 eigenvalues, they might be the same.
Right.
But then it has 2 linearly independent eigenvectors that go with it.
Okay.
Yeah. So I want to illustrate the cases of, okay, here's how some of the equations ODEs in the system are independent and others are not.
Okay.
So the system of ODEs, and I'm just going to make things easy and assume that the source term C is equal to 0. So we don't have to think about that. So we have W prime is equal to JW, but now I'm going to write out what that is. So that would mean that W1 prime is lambda 1 W1. W2 prime is lambda 2 W2. So those 2 equations are completely independent of the rest. So we know how to solve those. Then we have W3 prime is equal to lambda 3 W3 plus W4. Okay, how I'm getting this? I'm imagining a vector here, W1, W2, W3, W4, W5. I'm multiplying,
Okay.
I'm doing its matrix vector product.
W1, W2.
So I'll just draw a right vector here. It's not really supposed to be part of this equation, but just so you can carry out the multiplication.
Right.
Because I'm doing W, this is W prime over here, this is JW over here.
Right, so, it wouldn't really be given in that. I know you're saying you're imagining it's there.
Yeah, so I'm running it here so that you can try carrying out, like in your head, the matrix vector product
Okay,
to get these. So third row,
right,
I'm doing 0, 0, lambda 3, W3, plus 1 times W4.
got it.
Okay, and now I have two more equations. W4 prime is lambda 3 W4 plus W5, and then W5 prime is lambda 3 W5 and nothing else. You see where it's?
Yeah, I was trying to, the W4, it was, the four, you were doing the fourth row
Yeah.
on the whole thing.
Yeah.
Yeah.
Okay.
I don't know, why do I have, you wrote lambda 3, oh, they're all lambda 3s. I was writing them.
Oh, okay.
I was writing them as
Yeah.
lambda 4 and lambda 5,
Yeah.
so I was losing.
Okay. Each Jordan block is associated with one eigenvalue.
Which you said.
Okay.
I just wrote
Okay.
different, and
Okay.
it's all good.
All right. Okay. So now 3 of these equations we can go ahead and solve immediately, like we did last time. So W1 of t is e to the lambda 1 t W1 of 0, and the same for W2. And then W5. So in other words, the last equation in each Jordan block is independent of the others and can be solved immediately. So now for the other two, like we'll go to the fourth one. We can solve that next because now we know what W5 is. That's a source term for this equation. So now we can use the formula, so we can use this solution formula that was derived like sometime last week, I believe. So y is equal to e to the pt y of 0 plus integral from 0 to t e to the t p minus s q of s. Okay. So now I can use that formula so I'll do W4. So that's going to be, from a first term, we have e to the lambda 3t, W4 of 0. So it starts out the same way as the others, plus integral 0 to t, e to the lambda 3, t minus s, and then this evaluated s, e to the lambda 3 s. W5 of 0 ds. Okay. Which is actually convenient. Why?
Give me one moment.
Okay.
So because the s's are going, the e to the lambda 3 times s will cancel with.
Yes, with the minus s over
right.
here. Yeah, so that goes away, and that whole thing goes away. So that's e to the lambda 3 t but we're integrating with respect to S. So what's the integrand is actually a constant.
From 0 to t, t times w, or sorry, 5, 0, ds, okay.
So if a constant, I could just pull out, and that's e to the lambda 3t w5 of 0 times the integral. So if I pull out everything from the integral, what's the integral equal to?
Oh, wait, sorry, I was right.
Okay, everything here is independent of S.
Right.
Factor out everything.
Oh, we have to factor out everything. Yeah, okay. So, I mean, then the integral.
So what's left is 1 as an integrand.
Right, so just S.
Yeah.
Yeah, so T.
T.
Yeah.
Yeah, because it's
Okay.
S from
Right.
0 to T is T. Okay, so now, so now W4 is completed. Okay, so I'll just write down the final thing here. So plus T e to the lambda 3t W5 0. Okay. So this is what happens when these equations get coupled together a little bit, because before, in the diagonalizable case from last class, each w is just an exponential, e to a lambda t times the initial value. But now we have a t e to the lambda t. So that's what changes in this case.
Mm-hmm.
So now I can take this whole thing, this is w4 of t, and substitute it into this equation.
Yeah.
And apply the same solution formula to solve that.
Right.
So before we do that, any questions about what's happened so far?
Okay, so we did that for W4T, but that go ahead and replaces the source term there.
Yeah.
But
So
what would be the difference in us just, I mean, I guess, does it really matter if we just use the y prime equals py plus pt form and not do that?
okay. Well, I'm not sure what you're asking.
Like, what if we don't replace it? What if we just do the same thing again?
Oh, well, okay. Oh, for this, you mean?
Yeah.
Well, okay. But the thing is, at some point, we had to substitute W4 at some time. And we are going to use that solution formula to get W3.
Yeah.
So, okay. So,
okay, I gotcha.
All right. So W3 of t will be e to the lambda 3t W3 of 0 plus integral e to the lambda 3 t minus s times all of W4.
Right, okay.
Oh, that's evaluated s. You gotta be careful about that. So it's s e to the lambda 3 s W5 of 0 d.
Kept doing that on my homework.
Yeah. Oh, yeah.
That same mistake.
Okay.
Oh, S is, I keep thinking that S and 5 is mixed up. Okay, E lambda S. DS.
Okay. All right. So now for this, it's the same kind of simplification as before, because every term here is e to the lambda 3s, which will cancel to e to the minus lambda 3s over here.
Mm-hmm.
So that's gone, and that's gone. So the integrals will simplify considerably. I'll just write down what that turns out to be. So e to the lambda 3t I'll pull out. But everything else remains. So now there's a little bit more to do than before.
Mm-hmm.
So what will we get when we integrate this with respect to s?
Okay, we have W4 of 0. Did we get something with W4 earlier?
Well, before we had W5 was 0, but it was a constant, so I just pulled it out.
Okay.
But here is nothing I can factor out entirely. I mean, I could break this down into two separate integrals.
Right. But is W4 of 0?
It's a constant.
Also a constant? That's what I was getting
Yeah.
at, my bad.
Yeah.
So I guess we can go ahead and break it down and then, but I mean, if W. Yeah, I mean, we're just dealing with the constant plus S times another constant.
Right. So now when we integrate with respect to s.
Right, we're gonna get a t, it's gonna be W4t, right?
Yes, that will happen again.
And then plus s squared over 2
Yes.
doubled, yeah.
Yeah, so now we have e to the lambda 3t. So then we have, I'll just factor that out because it's in every term. W3 of 0 plus t W4 of 0 plus 1/2 t squared W5 of 0. And we're done. We've solved for everything now.
Wait, where was the W3 of 0 from again?
Oh, over here.
I see. My bad. I wrote that and then looked up and okay. Oh, and you factored it out of everything. Okay.
Yeah.
Got it.
Okay.
Times W3 of 0. I remember my glasses next time. T times W4 of 0 plus T squared over 2.
Okay. Now, in a diagonalizable case, the solutions that we get, W1, W2, W3, W4, W5, will all be the same, except for this term in W4 and these two terms in W5. So now what I'm going to do is I like to express the entire solution as a matrix times the initial data, which I can do because every term in here uses an initial value of something.
Right.
That's true in all 5 of these. So I'm going to do that. I'm going to contrast the diagonalizable case from last week with the non-diagonalizable case that we have here.
Okay.
All right. So any questions about this before I erase? Well, I'm going to take a picture.
Got it.
So WT, the vector, consists of all 5 unknowns I want to express this as a matrix times the vector of initial values of those 5 unknowns. So all I can do is I can look at W1, W2, W3, W4, W5 of T, those 4 formulas we just got, and see like, okay, what is multiplying each initial value? And that'll tell me what goes in the matrix.
I rewrote all of them
Okay.
first in order so I could actually.
Okay.
Okay.
Now 3 of these are very short. W1, W2, and W5 are just initial values times e to the lambda, e to lambda something times t. Lambda 1 in this case, lambda 2 in this case, lambda 3 in this case.
Yeah.
Now, this is the exact sort of thing we saw in the diagonalizable case. It's just an exponential times initial value, nothing more. But now, I'll section off the Jordan blocks again. But now for W4, we'll have e to the lambda 3t on the diagonal, and then t e to the lambda 3t on the super diagonal. And then for lambda or W3, we have e to the lambda 3 to the diagonal again. And then t e to the lambda 3t times W4 of 0 from our solution formula. And then 1/2 t squared e to the lambda 3t on the second super diagonal. So here are the diagonals. The main diagonal, first super diagonal, and then second super diagonal. Okay, so we can see a pattern there at least, based on what's on the diagonals. But now, the thing is, in a diagonalizable case, we were able to get from what we had here to a clear matrix exponential. So can we do that here? And for that, if we look at the Jordan block that we had, J3, which is lambda 3 in the diagonal, and then the 1s above it.
Okay.
Now, when we had just the lambda 3's in the diagonal, if we took the exponential of this, it was just e to lambda 3t down the diagonal. But now we have these 1s. So how's that going to affect things? So for that, we need an understanding of what powers of J3 look like. So, e to the J3t is going to be equal to identity plus J3t plus 1/2 J3t, the whole thing squared, and so on. So Okay. I'm running out of time, aren't I? Oh, I'm practically out of time. Yeah. Okay. So I want to work this out, and it would be really nice if we happened to get that. Although the way I was about to do it seemed incredibly tedious, I think there might be an easier way to do this. It's best I stop here. Yeah, so I'll continue this next time.
Oh, that's pretty cool.
Because those coefficients we have t, then 1/2 t squared. Those, we recognize those from the Taylor series of the exponential. You look at what's multiplying e to the minus 3t. 1t, 1/2 t squared.
Right.
And so on. It's just that there's only a 3x3 block, so we had nothing else. We ran out of room.
Yeah, so somehow that's kind of correlating up until the 0 point.
Yep.
Yeah.
Alrighty. You know what? It's actually not a good idea to use this Taylor series expansion of the exponential. This is a straightforward one, the Maclaurin expansion centered around t equals 0. But if I use a different Taylor expansion, then doing this will be a whole lot easier. Okay, that's what I'll do next
forget
time.
the e or the e to the j 3t is equal to, I didn't forget the Taylor expansion.
Yeah, we'll use a different one.
Okay.
But
Kind of.
yeah. Okay. Well, see you in a half hour in the class. Okay. Let's see. Well, at least this recording went well.